All right, class, let's talk about this last section of chapter 3, which is an application, a business application to exponential and logarithmic functions. And it's called elasticity of demand. So we've been talking about demand and profit and price and increase in price and decrease in demand, back and forth. So that's really what this section is also all about. So what is an elasticity of demand? Well, to talk about that, let's talk first of all about what is a mean, or what is a relative rate of change. So a relative rate of change is really simply the ratio between the rate of change of a function with respect to the function itself. So I called it RRC just to keep it faster to write. And it's, again, in your textbook as well, it's not an official name for it, but that's what I'm calling it. So the relative rate of change is simply the ratio between how a function is changing, right? That's what the derivative tells you, how a function is changing, the instantaneous rate of change in a function with respect to the function itself. So it's really a percent change, as we will see in the next few examples. So it does not have units. That's what's important about it. So let's see what this means. And I'll get back to this formula in a second. So let's say, for example, a type of computer, some laptop computer increased in price from $1,000 to $1,050. That's a change of $50. Well, it's a lot of money, $50. However, when you think about going from 1,000 to 1,050, it's not that much relative to what it already costed. So if you think about what did it change by, it changed by $50 with respect to how much was it in the first place, is $1,000. So that's really a percent change with respect to the actual value. Yes. So if you divide these two numbers, you get a 0.05, which is 5%. So the price of the computer increased by 5%. Now, if you, let's say, take a scientific calculator, they used to be $15 and now it's $18. I know that's just the change of $3. However, when you think about what 3 means relative to what it used to be, so in other words, the amount of increase with respect to the original price, so $3 versus the $15 they used to cost, that's divided as a 0.2, which is a 20% increase. So really, if you think about it, the calculator really increased in value or in price a whole lot more than this computer. It went up 4 times as much, really, as the computer went when you think about percentages. So that's what a relative rate of change is. It's just simply a percent change, or an amount of change with respect to the original amount. Okay, so it's a percent. So let's say, given this function right here, find the relative rate of change in this function and then evaluate it at t equals to 5. So what does it mean to find the relative rate of change in a function? It means to find how much did the function change by, right, with respect to how much it was. And that's in general. So of course, at certain times, the function could be changed faster, it could be changing slower, right? So it all depends on where you're looking at. So in this case, it's going to depend on the variable t, or maybe not, who knows? So so all we have to do is take the derivative of this function. So what's the derivative of that function? Well, again, we will keep the coefficient of 1,000 times, move on to take the derivative of the e part. So remember what I had said, the derivative of a natural exponential function stays the same. Times, however, we need to move on and take the derivative of the exponent. So the derivative of 0.07t is just 0.07. Okay? With respect to what the actual function was. What was the actual function? Well, 1,000 e to the 0.07t. So really, if you look at this, you don't even really need to compute much, because what's going to happen, the 1,000 stayed the same, so it gets to cancel out. The E stayed the same, so it gets to cancel out. So you're left with a 0.07, which is really 7%. Now, even if you should substitute in a new value in it, which is 5, if I'm going to substitute in a 5 in 0.07, well, there is just a 0.07 left. So it really doesn't matter what T was, because this answer turned out to be a constant rate, right? So it's a constant value. And it's true that the exponential function is the one and only function that increases at a constant rate. What's the rate of increase? 7%. So that's what an exponential function. Every time period, whether it's every day or every year, depends what the time means in this specific function. For every period of time, let's say yearly, every year it increases by 7%. It increases by 7% of what it now is. It increases by 7% of what it now is. So exponential functions are the only ones that have a constant rate of change. So it doesn't matter what value T we're plugging in, the answer is the same. Now, I put this aside in the textbook. I don't really want to bother you with it, but just so you'll see in the textbook, I usually don't solve the problems this way. Just think again, what is a relative rate of change? It's a derivative with respect to the function itself, right? By how much does a function change with respect to what the function was itself. But if you're looking back at our section 3.3, you will notice this formula here. And what did this formula? The derivative of a function with respect to the function itself. This was a formula we saw for the logarithm of a composition of function, right? So the ln of a function. So really, one other way of looking at this, and really I honestly don't even want to bother you with it, but it's in your textbook. Many teachers and many textbooks teach it this way. That's the same thing as the derivative of this function, okay? So what you could also do is you could take the log value of the function itself first and then take the derivative. So I've done one example like this in class, again, in the textbook, so don't worry about it. So if you take the logarithm of that function itself first, and then take the derivative of it, well, what's ln of that? So first of all, a logarithmic function, a log of a product turns into sum of the logs. So if anything, it kind of shows you fine why we talked about the properties of logs, because if anything, you can, well, maybe use it to simplify something. So let's make sure that what we're talking about is not in vain. And then we're taking the derivative. So again, I use the properties of logs on the inside, and I split the log of a product into the sum of logs. And now I want to simplify it a little bit more, because as you see, what else does a log and an e do? They cancel each other out, okay? So now when I take the derivative of this, what do I get? Whoops, here, t. The derivative of a constant goes to 0, and the derivative of 0.07t is just 0.07. So as you see, we're getting the same exact answer as I got here, but honestly, I find that this is way more work. This is just the same. I mean, we got this quite fairly easy. So I just wanted to point that out, because many textbooks and many instructors make you take the log first. But I think it's just more important to understand what a relative rate of change is. And a relative rate of change is the ratio between how a function is changing with respect to what it was, period, done. The computations aren't that complicated. Good. So we're going to put this relative rate of change to good use to talk about a really important application in business, which is the elasticity of demand. So one more time, the demand is a function that gives us the amount of units the consumers are willing to buy at a price P. So we've done several problems lately about this. So the demand is the number of items or units purchased or sold at a certain price, yes? Now, Sure enough, we've also talked about this, that if you increase the price, what's going to happen to the demand? So if you increase the price, the demand is going to do what? It's going to go down, yes? They go in opposite directions. Make the price higher, we're going to buy less. Make the price lower, so if the price is decreasing, what are we going to be willing to do? We're going to be willing to buy more. So all I'm saying is that they go in opposite directions, and I've been saying this quite a bit lately. What we're interested in, though, is how much these changes are relative to each other. So in other words, if you're going to increase the price by a lot, does the demand go down also by a lot? Or not so much? Because if you make the price way higher, but only just a few less items are being purchased, in the end, you're going to make more money because, again, what is the revenue, or how do we make money, or how do the producers make money? How many items we're buying, yes, so the demand times the price per item, yes. So ultimately, what we want is increased revenue. So fine, we're going to charge more, we're going to buy, people are going to buy less, but the point is, once you multiply these numbers, when are you going to make the most amount of revenue? So the question is how are these changes relative to each other, right? Do you increase the demand a lot? Do you increase the price a lot, but the demand only goes down a little? Well, that's a good thing. You increase the price a little bit and then there's a big drop in demand. Well, that's not a good thing because you're going to buy a whole lot less, you're going to sell a whole lot less items, and you're only charging a little bit more for the item. So we want to find that best balance so that we can increase the revenue. Okay, hope that makes sense. Okay, so I'm going to move on finally. And here, given a demand function, what is the elasticity of demand? So as I said, the elasticity of demand simply measures how are these changing related to each other. Do we go a big change in price? Does that make a small change in demand, right? Or backwards? So that's exactly what we're going to be looking at. So the elasticity of demand, we call it EFP, and it depends on the price, right? I'd say. So the elasticity of demand is the relative change in demand with respect to the relative change in price. That's how we measure that. Now I'm going to talk about the minus sign in a minute. So what's a relative change in demand? Well, it's the derivative of the demand function with respect to the demand function itself, right? We just said relative change in a function is the derivative with respect to the function itself over the relative change in price. So it's the derivative of the price with respect to what the price was itself. Now, I have this minus sign, and you're going to tell me why I have a minus. Because, as we just talked about, where did I put it? Here. As we just said, the price is increasing, the demand is decreasing. So one's going to have a positive slope, but the other one's going to have a negative slope. One's going to have a negative slope, the other one's going to have a positive slope. So every single time, one of these quantities will be positive, one of them will be negative. So this ratio will always be a negative value. Now, it's much, much easier to look at positive numbers. So all we're doing with this minus is turning this negative answer we would get back into a positive, just because it's easier to compare positive numbers to each other than it is to compare negative numbers to each other. It's just easier computation. So that's why the minus sign. Okay, all right. So I'm going to continue this calculation. So that's where the minus comes from. Just to make the answer pretty. Now, remember, when you divide by a fraction, you multiply by its reciprocal. Okay, so there's that. Okay, the other thing is P is your variable, right? It's just like your X. So what is the derivative of X? The same thing as the derivative of P, or whatever you call your variable. This is going to equal to 1, right? The derivative of just X is 1. Remember, P is the name of your variable. So putting this together, you get this formula that says P times d prime of P divided by d of P. So this is the formula for the elasticity of demand. Okay, so I can write it one more time for you. We're going to use it in the next example. So it's negative P times d prime of P divided by d of P. Okay, now it is really easy to figure out the answer or figure out the formula. It's simply the relative change in demand with respect to the relative change in price. I just divided these two fractions. So if, in case you forget the formula, all I'm saying is it's really easy to figure it out. So remember, now because we changed the sign, we're getting a positive value every single time. What we're going to simply do is compare that positive value to 1. So if E comes up to be less than 1, in other words, the change in demand is less than the relative change. So the relative change in demand is less than the relative change in price. So this ratio is a value less than 1. So in other words, what? The demand, in other words, the consumers, the amount of items that the consumers are buying are not changing as much as the price. So a big change in price only makes a little change in demand. So what should you do? Definitely, you should be raising the price. Because if you raise the price by a lot, the change in demand is only going to be a little. So you get to sell your items at a higher price, and fine, people will buy less, but it's a lot less than what you would expect, right? So the demand goes down only a little. Now, if the elasticity of demand is more than 1, then what? The consumers are answering strongly to the change in price. So even if you change the price by a little, the demand is going to change by a lot more. So what should you do in this case? In fact, you should be lowering the prices. Why? You lower the price, what happens to the demand? Will go up. And will go up by a whole lot more. So even though you're charging a lot less for your items, yes, even though you're charging a lot less for your items, a whole lot more items are going to be purchased, okay? So that's what the idea is, right? So if the demand is elastic, you will be lowering the prices. So the way to remember this, I just explained it why that is so. But just the way to remember it, less means more, more means less, right? So that's what you should do. Now, what if the elasticity is 1? Then that's perfect, by the way. Once the elasticity is 1, you got the perfect balance between price and demand. So that's really when your revenue will be maximized. So you want to find where the revenue is being maximized in a demand price situation. Just think about and figure out where the elasticity is going to equal to 1. And that's where your maximum will occur for the revenue. So if E is 1, we said demand is unitary, and it's 1 at critical points of the revenue function. So when E equals to 1, just as I said, the revenue is at a maximum. Okay, so that's to maximize revenue. I'll write it one more time here. The elasticity of demand has to equal to 1, okay? So how do you find the elasticity of demand? Right here. Now, of course, how else can you maximize revenue? Take the derivative, set it equal to 0, no big deal. But yes, that's another way. Okay, so here it is. It says, given the demand function, here it is. It's a function, made up function. Find the elasticity of demand at a price of $5. So one more time, here's our formula, okay? The elasticity of demand is equal to negative P times d prime of P divided by d of P. So for our function, this is going to be, so all you really have to do is take the derivative of this function, otherwise copy the rest. So the derivative of this function, well, the derivative of 300 is going to be 0, yes. minus 3p squared, right? So that's the derivative, divided by the function itself. Okay. Now, don't be crossing anything out. This is a product, but this is a difference, so there's no common factors. However, what can I do? I can definitely multiply these two values. So see how I have a negative times another negative that makes it a positive 3p to the third over 300 minus p to the third. So as I said, don't go reducing anything. This isn't a product, so you can't reduce common factors. This is not a product. Okay, however, it says find specifically the elasticity of demand at 5. Okay, so let's plug in 5 into this function. So I have a 3 times 5 cubed over 300 minus 5 cubed. So put this in your calculator, it's 125, 375 minus 125, that's 175. So whatever this is just, I don't even really care what it is, because all I want to know is this value more than 1 or less than 1. So sure enough, it is more than 1. So this being more than 1, what should you do with the price? More is less, remember. So you should be lowering the price. So from this price of $5, make it lower, right? Now, what should it be? Well, it should be whatever it is to make what is the best price that you should make. Whatever the solution to when this elasticity of demand would equal to 1. So if you want to find the ideal price, just set the elasticity of demand equal to 1, right? Cross multiply, solve for p, easily done. We got our last problem, we're going to do that. Okay. All right, so it says the demand for a certain type of wine is, here it is the function. Find the elasticity of demand at a price of $15. Should you lower or raise the price? Okay, no problem. Let's see. So find the elasticity of demand is negative p times the derivative of p divided by d of p itself. Now, sure enough, I'm going to take this function aside here. It's 10 over p squared, so what would be the best idea for it? Sure enough, to take that p and make it a negative exponent, right? Take that up to the top. So now taking the derivative of this function, it's going to be a negative 20 p to the negative 3, yes? Over, I'm going to leave it not as a fraction, but as negative exponent. So the function itself is still the 10 p to the negative 2. So I'm going to put the top together. I have a negative times a negative that makes it a positive 20, and p times p to the negative 3. Remember, that's a p to the 1. So when you multiply numbers with the same base, you add up the exponents. So 1 plus negative 3 is a negative 2. And as you very well see here, there's the same amount of p's in the denominator and the numerator, and 20 divided by 10 is a constant, 2. Okay? So, what did we want to do? Find the elasticity of demand at $15? Yes? Well, again, 2 is 2. There's no p to plug in like before. There's quite a lot of variables left. But none here in this case. Again, there's a product here and there's a product here. So that's why we got to reduce common factors. So this is more than 1. So what should you be doing again? You should keep lowering the price to wine, sure enough. Duh. Just kidding. All right. Always a good idea. So lower the price of wine. Okay. So there it is. There's this problem. Okay. Okay. I've got 2 more. So it says right here, let's put this up a bit. Better. It says the price for one of the Seattle ferries. Let me get where. Okay. That might be better. Okay. Just adjusting. So it says the price, but again, you have the notes in front of you. You just need to see me how I solve these problems. So I know you have the notes. And again, you know you have the blank notes on Canvas, and you also have the filled up notes on Canvas. but it's best to, yeah, just follow this with the blank notes, and then in case you, whatever, you have them both, but try and solve these problems alongside with me. So the price for one of the Seattle ferries is currently $5. The demand function is given there, where P is the price of the fare. The city is planning to raise the price. What would you advise them to do? Well, that's a good question. Maybe they should pay us a whole bunch of money and then we'll advise them. So here it is. Sure enough, I'm going to take that function one more time. And what am I going to do with it? I'm going to rewrite it because I know I'm going to end up having to take the derivative of it. So I need that power form of it. Okay. So I want to know if I should be raising the price or lowering the price. So I want to know, how is the public responding to my change of price? Okay, so that's the demand with respect to the price. How will it be responding to my change in price? So the elasticity of demand is going to be a negative P times the derivative divided by the function itself. Great. So it's negative P times, what's the derivative of this function? So sure enough, I have a coefficient, which I'll keep, times the derivative of this part here. I have to use the power rule, so it's 1/2 times 12 minus P to the negative 1/2. And sure enough, this is going to be a chain rule, so you need to go inside the function and take the derivative of the inside of it, and the derivative of 12 minus P is a -1, right? For the -1 times P. So don't forget about the chain rule. Divided by the function itself. Okay, so let's see what things we can put together here. First of all, this negative times this -1 at the end, that's going to make it a positive value, yes? So that turns into the positive. You don't really need to multiply 20,000 times 1/2 and then divide it by 20,000 again, just to find out that 10,000 divided by 20,000 is 1/2. Okay, so I'll keep it that way. The P I'm going to leave at the top. And then I have this parenthesis here that has a negative exponent. And as I keep bugging you, what do we do with expressions with negative exponents? We throw them back on the bottom to make them positive. So when this guy comes down to the denominator, it's going to have a positive 1/2 exponent, yes? So I got the 1/2 written, I got the P written, and now what is 12 minus P to the 1/2 times another 12 minus P to the 1/2? And if you said 12 minus P, you would be completely correct because the bases are the same, and you add up the exponents, and 1/2 and 1/2 makes a full 1, right? So there you go. That's the elasticity of demand. Great. What do I want to do with it? I want to check it at this price of $5 that we are currently, or the city of Seattle is currently charging. So I'm going to put in a 5 for P. So that's a 5, and that's a 2 times 7. So sure enough, I don't even care what, obviously it's 14, but no big deal. This fraction is going to be less than 1. That's what we're interested in. So if the elasticity of demand is less than 1, what should you do with the price? Less is more, so increase the price. Sure enough, you should be increasing the price. You could have said that without solving any of these problems. Just kidding. What are they going to do? Swim across the bay? They have to take the ferries. There's no other way across all those islands many times. Yes, there are some bridges, but many islands are only reached by ferries, so there's that. Okay. Okay. So the last problem here, it says a bike manufacturer is selling bikes at a price of $250. So this must be our price, our given price that we keep talking about. The demand function for these bikes is given by this function right here. Okay, so we have the demand function. Should the dealer raise or lower the price? And then, as I just promised you earlier, what we're going to do is we're going to take this problem one step further and figure out which price would lead to a maximum revenue. Okay, so first things first, lower or raise the price? Well, we have to find the elasticity of demand. So here's your formula one more time. Now, I don't need to change anything. This is already an exponential function. Yes, it's got all the parts that I want. So the derivative of this function here, I'm going to keep the 10 for the coefficient, times, move on. And the derivative of this, I'm going to use the power rule first. So the 2 comes up front. So 300 minus 0.3p to the power of 1 times, move on and take the derivative of the inside of this parentheses, so that's going to be a negative 0.3. Okay, all over, the demand function was 10, 300 minus 0.3p to the power of 2, so that's that. Okay, so let's see if we can put some things together. First of all, 10 and 10 are going to go away. This is the same parentheses, once with a power of 1, once with a power of 2. So what we're going to do is just be left with one of them. So if I put all this together, this negative and this negative will turn things back positive as promised. 2 times 0.3 is 0.6 of these p's. Yes, that's what's left. And as I said, the bottom just has one more of these parentheses. Okay, so that's the elasticity of demand. Great. Okay, what's next? The price right now for the bike is $250. So let's see how the consumer is going to respond to a change in this price. So it's 0.6 times 250 divided by 300 minus 0.3 times 250. So put this in your calculator. I have it, I know I have it. So the answer for this is going to be 150 for that, over 25, by the way. Okay. 0.3, that's 275. It's 225, right? Wait a minute, what did I do? 300, yeah. Oh, okay, I had changed it to 300. Good. So that's 225. So 225, let's see, did I do that right? I need a calculator because I changed my numbers, it looks like, from the old notes. So, or the ones I used to have here. So 6 times 0.6 times 250, that's 150, that's right. And then, yeah, so 0.3 times 250 is 75, as I said, minus that out of 300 is 225, so that's less than 1. Okay, just double checking. So less than 1 means, again, raise the price. Okay, so good, we can raise the price. Okay, what should we raise the price to? That's the question. Which price would lead to a maximum revenue? Well, the one where, as I said, the elasticity of demand is going to end up equaling to 1. So this is the equation we want to solve. So when is 0.6p over 300 minus 0.3p going to equal to 1? Well, cross multiply, as I've done to many of these problems. Get the p's to one side and divide by 0.9. So what should be 300 divided by 0.9? Make it $333.33. So that's the best price out there, okay? Where the manufacturers are going to make the most, or revenue, yeah, the highest amount of revenue. Okay, so we're done.